I'd like to welcome everyone to session 3 of Understanding the Generation Time for COVID-19 workshop. Today, this morning, we have two fantastic speakers, and I'll go straight into introducing our first speaker. So we have Lorenzo Pellis from the University of Manchester, and Lorenzo is going to tell us about within and between host modelling, so lessons from other diseases. Okay, over to you. Thanks.
Thank you. Can you see my screen?
Yeah, we can.
Okay, perfect. So, thank you very much to everybody. Thanks to the organizers for inviting me. I was asked to kind of present some of the stuff on the generation time, but from a slightly different angle, because I work quite a lot, especially in the past decade, on models across multiple scales within and between hosts, but also within and between, also within the host at multiple scales, which is what I'll try to describe later on. I'm in Manchester. I'm a Sir Henry Day Fellow. I'm part of the Juniper Consortium and the Alan Turing Institute. So I'll briefly start with an introduction, and then I will try to basically this talk is an appraisal of models, so-called time since infection, which I'll describe briefly. And I would like to explain why I find them useful, especially in the context of HIV, through the means of two examples. And then I'll discuss some open challenges. So in terms of within host dynamics, which is the part of the theme of this talk, any model you construct makes some assumptions about what's happening within the host, whether you want it or not. And this has been said quite a lot by Julia yesterday as well. Even just a simple transition model is basically making some assumptions about what happens within the host, even if it's very simple. So within host dynamics are typically described as transitions between states with ODEs. The model is simple. The limitations are obviously constant rates, exponential waiting times, all stuff that has already been discussed. So I'm going to go fairly quickly here. You can make the model more realistic. You can put multiple compartments in parallel or in series, and you get all sorts of either long chains or phase type distributions if you put together compartments in series and in parallel. And you might have different effectivities in different compartments. The problem is that the number of compartments can grow quite fast, but ODEs solvers that handle large number of equations are very efficient. So this is typically done. And this is an example of the model we in Manchester and Oxford and Lancaster have been using for COVID-19. And this is just, I don't want to go into the details, but this is just an example of a model with many compartments where people are asymptomatic or they get infected, they become symptomatic, first latent phase, then they become infectious but not showing symptoms yet, then they enter into a late infectious stage, or they can proceed to hospital and they enter into various hospital compartments which are here, so that you can actually match them with the data on hospitals we have, and people might die or recover. This is just to show that these models are constantly used also on real-time assessment of the pandemic. But when people talk about generation time distribution, a more natural framework, at least in my mind, is to use these time since infection models where there is an infectivity profile, beta of tau, that describes the rate at time tau since the infection of an individual, at which the individual makes infectious contacts with other people. And the total number of infectious contacts, so the total infectivity of an individual, is the area under this curve. And then every contact, if you assume a contact is happening, the time at which that contact happens since the moment of the infection of the individual is given by a probability distribution that has the same shape as this curve, but is normalized to have integral 1. And that's the so-called generation time distribution, or generation contact interval distribution, infectious contact interval distribution. Different people use different names, obviously. And analyzing these models has been probably discussed by Julia yesterday, but you typically now work with the incidence rather than the prevalence of infection. And the incidence of new cases infected at time t occurs because people are susceptible, so there's a fraction of susceptibles in the middle of time t, and susceptible individuals are challenged by infection from people that were infected tau units of time ago, who now have infectivity beta of tau, and then you integrate over all possible times in the past. this gives the full dynamics. If you linearize to look at for exponential, the exponential growing phase of the epidemic, then the entire population is susceptible. For example, you obtain this renewal equation. If you plug exponential solutions in it, you obtain this equation that Julia showed yesterday, the so-called Euler-Lotka equation, where you have the Laplace transform of beta on the left-hand side, and the growth rate is that value such that the Laplace transform of beta equals 1. Because R naught is the integral of beta, then it's easy to see that R naught equals 1 is the same threshold as little r equals 0, and you can do some nice maths with it. But notice that typically in these models, everybody, even if the model is stochastic, everybody's assumed to have the same infectivity profile, which is not exactly the same as what people do when they assume a compartmental model, where people have a constant infectivity and an exponentially distributed duration of infectious period. So different individuals have different duration of infectious periods. So this curve differs between different individuals. So there is one way of capturing everything within a single model is to kind of allow these curves to be a random curve. So for example, now capital beta of tau is actually, could be either a set of curves, and you can pick one of a small number of curves with a certain probability. You can have a density of potential curves. So these models are therefore more general, but has some drawbacks. They are harder to study. They lead to partial differential equations or integral equation, delay differential equations. They are computationally more intensive to integrate, and they require initial conditions that are defined on an entire integral, the entire support of this distribution here. So part of my talk will be why time since infection, and if they are more difficult, do we really gain something if we go with them? And one, well, first of all, I just said they're more general, and that might satisfy some people just by itself. Then they can be closer to the biology or the experiments. For example, we might be interested in the detailed time evolution of the infection is deemed important for the particular problem we have at hand. And this could be, for example, the case of contact tracing, or when you study, for example, in the case of COVID, how to keep COVID out of small closed settings, for example, a care home or so on. And so you want to test people when they come and visit the care home. So the time of the testing, when the testing gives a positive result if you're infectious, and the time of your infectivity might be extremely important for keeping infection out. They are also very useful, and this is what I will talk about the most during this presentation, when you have long infectivity profiles or complex infectivity profiles, like in the case of HIV. And they might be useful because you have available data on them. You have information about how the viral load is changing over time within the host, and you have any other sorts of data. In the case of influenza, for example, there are studies that discuss ferrets challenged with multiple strains of influenza at different times. I don't want to go into details, but basically the outcome of the second infection is, and possibly also the first infection, is highly dependent on when, or the relative times in which one infection was introduced compared to the other. So there might be data on that as well. But the two things I want to discuss more carefully, if I mean some examples, are why this, one of the reasons why these TSI models are helpful is to include some more complex within host dynamics and match them to a model of transmission at a between host level. So there are many models of within host dynamics. These are just some examples. I don't really want to go into too much detail, but you have models with susceptible cell, infected cells, and free virus, for example, where there is no immune system explicitly modeled, or you can model the innate immune system, or you can model the innate plus the adaptive cellular immune response. And these are all examples that have been used for dengue, but only at the within host level. The first example of a model that has two scales put together is down to Gilchrist and Sasaki, where they had this really simple model within host dynamics, where you have one variable describing the pathogen load and another variable for the level of immunity, and you have just a competition between basically the immune system and the pathogen. And this is embedded into a between host transmission dynamic model, where you have the susceptible individuals that are born susceptible, they get infected roughly in the same way which was described before, and they die. And then individuals who get infected, then they progress in their infection, both in terms of time and in time since infection, and the immune individual then are also modeled explicitly. And now the transmission rate as a function of time since infection is assumed to be proportional to the pathogen load within the host. That changes as a function of time since infection according to this within host model. And notice that this is a very simple link, and one of the main challenges I will describe about this model is exactly this link between the two scales, which is often assumed because information on this link is rarely directly available. Pugliese and Gandolfi then tried to kind of expand on this simple within host model, making it more complex, but still leaving it as simple as possible in terms of the number of variables. We still have only the pathogen load and the level of the immune system, in this case, specific immunity. And they have another term, but basically they still try to keep it as simple as possible, but now they have a larger range of potential within host dynamics, where following introduction, an individual's infection could die out really quickly, depending on the parameters, in which case the individual basically has not been infected, has managed to kind of fend off the infection, or it can cause an outbreak within the host, so a proper infection, and then the individual recovers, or it might just grow unbounded, in which case basically the host dies. Another use of the time since infection model is down to the fact that they can enhance the understanding of more complex models. And I would like to show this by means of an example. This is a within host model of HIV, which was developed mostly by Katrina and Christoph. I mostly help with the mathematical part of it, and the motivation for it is the following. We have, so if you look at an HIV infection in an untreated patient, this is roughly what happens. The virus enters the host, then there is an initial phase called the acute phase, where the virus replicates really fast. And at some point, the immune system kicks in and brings the virus down, but doesn't manage to get rid of the virus. So the virus lingers around, trying to avoid the immune system all the time, and remains at low levels, where it's kept at bay by the immune system. But in the meanwhile, it's just destroying the immune system. And after this really long chronic or asymptomatic phase, because there are not many symptoms because the viral load is very low, then the immune system collapses and the individual develops AIDS. So there is the acute phase, the chronic or asymptomatic phase, and the acute phase. And now I'll introduce a term that I'll use throughout the entire talk. So it's a bit of a strange term for those not used to it, but this is the set point viral load is defined as the roughly stable value of the viral load throughout this chronic phase. And you can see the viral load might oscillate a little bit, but around a roughly stable value. And these oscillations are much smaller than the variability that is typically observed in the set point viral load between different individuals. Okay. And one of the questions we were trying to answer with this model was how can we explain such a huge variability between individuals? Because this variability is really huge, at least 4 orders of magnitude between different patients. Some patients are at that level, some patients are at that level, and they remain in that condition throughout their entire chronic phase. So what is causing this variation? And there are 2 things that could cause that. One that are the most natural explanations. One is about the properties of the virus. Maybe the virus replicates faster and leads to a higher set point viral load, is better at infecting new cells. Or it could be down to the individual. So the efficacy of the immune response, and I'll use this term CTL for cytotoxic T lymphocyte. This is basically like the strength of the immune system. And the problem is that if you imagine that the body is a well-mixed bag of susceptible cells that get infected, viruses that replicate faster might take over the host faster, so the dynamics could be much faster, but typically the steady state at which you reach in models like that is only very mildly affected by small variations in the virus replicative capacity or in the strength of the immune system. And so typically you have a region of parameter space with two variables, the strength of the immune system and the strength of the virus, where if the immune system is better, you basically clear the infection. If the virus is better, then you essentially you reach the steady state, and there you are. And there is only a very, very narrow strip in this parameter space where you can get a lot of variation in this steady state for small variations in these parameters. So what questioning was the well-mixed assumption is an assumption because the virus does not replicate uniformly throughout the body. There are some regions like lymph nodes where the viral replication is focused, and we estimated that there are between 1,000 and 10,000 of these sites of replication in the body. And you can see also genetically that might be a case. So this was basically suggesting to develop a metapopulation model of within host infection. And this is what we did. So imagine there are multiple patches, a site of HIV replication. Susceptibles are just flowing into the patch and out of the patch, and the immune system cells are coming into the patch and out of the patch, and they just transit normally. But if an infected cells appears in a patch, then the immune system cells are prevented from leaving the patch and start accumulating. And so you have more infected cells, more CTLs, but also now you have infected cells that leave the patch and can reach another patch through the blood. In addition, there's an extra complication, but HIV is characterized by the fact that some cells that have been infected by the virus and suddenly go into a quiescent phase. So the virus is not expressed anymore, the cell doesn't replicate, the virus doesn't replicate, it remains hidden. Essentially cannot. So we say that average. So I'm not going to go to the details of the equation, but basically we can write a system for the susceptible cells in each patch I, the infected cells in each patch I, the infected cells in the blood, and the number of CTLs in each patch I, and the number of infected cells in the patch from the blood. If we pretend we make where into the patch enters into that patch since that moment, we can simplify the equations and we can look at this analytical approximation where the immigration of infected cells is negligible after the, and we can think of how the within patch dynamics are giving you a certain number of infected cells within the patch, and these cells can then leave the patch either with a rate epsilon at which they leave the patch. This is the probability that an infected cells that have left the patch successfully reaches another patch without being killed while in the blood stream. And so this term here, beta p of tau, actually represents the average number of patches a single patch can infect as a function of time since the infection of that patch. And if we can write some dynamical equations for this system of patches, then we obtain exactly the same equation we were describing before. So the incidence at which new patches get infected is down to the fraction of susceptible patches times the infectivity coming from all other patches infected tau units of time before. And we can work out a patch-to-patch reproduction number. And if the RP is less than 1, then there is no infection in the entire system. So by looking at the three possible outcomes of the within patch dynamics, we can obtain three different results at the population level. So there is either RP is less than 1, in which case the virus disappears from every patch and we reach a disease-free equilibrium, or even at its strongest, the immune system cannot remove the virus from a patch. And so the amount of infected cells in a patch reaches a steady state. And this leads to a full equilibrium where every single patch is at the steady state. And the entire organism is a steady state. And we call this the full equilibrium. Or we could be in a situation where every patch has an outburst. The immune system can stop this within patch outbreak, but it takes too long for this to happen, and therefore the patch has enough time to seed the infection into other patches before being cleared by the immune system. And so the patch-to-patch reproduction number is greater than 1, but less than infinity. And this leads to a third steady state, which we call the shifting mosaic steady state, borrowing that term from ecology, where after a catastrophe, you can have different areas of land that are a different phase of their regrowth process. And in this system, basically, in this steady state here, this intermediate steady state, we have a situation where the entire organism is at a steady state, but this is the result of a highly dynamic process of burst within each patch that then is stopped, but by that time the patch has infected other patches. So in the full equilibrium, the number of infected cells in the body remains at a stable value, and within 2 randomly selected patches, it roughly oscillates because it's a stochastic model, but it's roughly stable, and the immune system is always at its maximum. And instead, in the shifting mosaic steady state, then roughly the total number of infected cells in the body remains more or less constant with some small oscillations, but these 2 randomly selected patches that show a highly dynamic process of outburst and clearance, and the immune system in each of these patches is always activated and then relaxes and activated again and relaxes. And you obtain, this is a video that I'm sure Katrina would have liked me to show, because this is one of the only few videos that I ever made in my career. So this is more or less how this shifting mosaic steady state behaves within the organism, and this process is this steady state exists only if it's metapopulation model. So basically, this steady state exists only if you consider a metapopulation model. And the reason why this result was important is because, as I said at the beginning, small variations in the viral replicative capacity or small variations into in the strength of the immune system only lead to small variations in a steady state within each patch. So they cannot explain why you see so much difference in this chronic phase between different individuals. But if we are at this, if this shifting mosaic steady state is what really represents what happens during a chronic phase, and it's very difficult to kind of verify experimentally this is the case, but this is a potential explanation. What happens in every single patch is more or less always during this exponentially growing phase, because after a while, then the immune system obliterates it. And the slope of this curve, the speed at which the virus grows during this exponentially growing phase, is extremely sensitive to really tiny variations in the virus replicative capacity. And so you can achieve much more variation in the overall number of infected cells at the individual level, at the host level, for small variations in the parameters. This is just further example of this. But so assuming there is no reservoir to keep it easy, in a single patch model, you either have complete clearance or you're in the steady state. And in this metapopulation model, either in the approximation or in the simulation, you can see how if you fix a certain strength of the immune system and you change the viral replicative capacity, you go from a state where no cells are infected to a relatively large region of the parameter space where you can have a wide range of total number of infected cells before reaching the full equilibrium. While the model with a single patch, which is this black line, has this really, really sharp transition and doesn't explain this intermediate levels of viral load that can be seen in some individuals. And if you add the reservoir, you can get even more flexibility. End of the example, the first example, where using these models can enhance understanding of more complex models. And then for using the time-series infection models I would like to describe, these models, so they require a bit more thinking about which assumptions are responsible for the results that we see. I'll try to describe this with a different HIV model. This is a model of HIV within host dynamics and between host transmission. goes back to some work that Christoph Fraser and others did in 2007. But let's start again from this graph. So again, let's repeat. There is this acute phase with a high infectivity. Then there is this chronic long phase. The set point viral load is this average, roughly stated value of viral load during this long chronic phase, and then you develop HIV. And it's possible to see the set point viral load actually, it's predictive of infectiousness in the sense that individuals with a higher set point viral load transmit more. So there's a higher chance of transmission for those that have a higher set point viral load, but also individuals with a higher set point viral load do AIDS faster. And so, by the way, this chronic asymptomatic phase, if the individual is untreated, up to like a couple of set point viral load is very high, but if your set point viral load is very low, it can last 10, 20 years. So the fact that you're more infectious, but you live a shorter life led Christoph Fraser and others to, well, imagine that therefore there needs to be an optimum intermediate set point viral load where you are actually maximizing the amount of total infectivity that you're spreading throughout your infectious life if you're untreated. And then by observing viral load, the heritability of set point viral load between infections is high. And well, this is a bit out of date now, but has been in the system observed at the time, it was steadily increasing for decades. And it seemed to have plateaued and stopped evolving. Might have suggested that there has been some evolution that has brought the set point viral load in that population to reach a value that is roughly close to the maximum value for the transmission potential curve that you would have multiplying these two together and observing that the maximum is in the middle. This led to the hypothesis that the HIV is evolving at the population level to optimize its ability to transmit between individuals. And we call this the long-sighted evolution. However, this sits uncomfortably with the fact that viruses that replicate slowly tend to lead to low set point viral load, and viruses that replicate fast tend to lead to higher set point viral load. And an HIV infection lasts for decades, so there is ample room for within-host evolution of the virus, which should select viruses that replicate faster within the body. However, we call it short-sighted evolution because then that would lead to very high values of set point viral load, and that is detrimental for survival of the virus at the population level in terms of transmission between hosts. So by putting together these two scales, we can actually invest the conflict in terms of the evolutionary conflict between the within host scales that will push towards really aggressive viruses and the between host scales that would suggest something intermediate would be optimal for survival in the population. So try to develop a model like that. So I'll briefly describe this model. Deterministic susceptibles are identical. I'm assuming homogeneous mixing and dynamics described by the fact that the total population size grows because of a total birth rate and dies because of a per capita death rate. Now, on this population, I put an infection, and this is an SI model because we assume that HIV, you don't recover from HIV, and individuals just die after the end of their AIDS phase. And the infection, we assume, this is a simplifying assumption, we assume that the infection is caused by a single virion, J. So an individual is called an individual of type, a case of type J, if it's infected with a virus of strain J. And we assume that there is your infection is determined by a single virion, which is not unrealistic. We also make the assumption that the infector strain that infects you determines your set point viral load. So strains that replicate faster lead to a higher set point viral load. But as I described before, individuals with a high set point viral load are more infectious, but also live a shorter life because they have a shorter asymptomatic phase, short chronic phase. So the set point viral load actually determines how your overall infectivity profile looks like. And then we try to describe this function, beta ij of tau, that describes the rate at which a type J case transmits strain I and therefore generates new I-type cases. So an individual is infected with strain J, the rest within host evolutions, many of strain J is transmitted in many cases, but then within host evolution leads to, for example, the transmission of a slightly different strain, so someone else gets infected with strain I. And these are the equations. I'll go through them a bit more carefully. So this is the incidence of individuals of type I. So these are the individuals that get infected with strain I at time t. And this is the fraction of susceptibles. And now individuals get infected with strain I if they are susceptible and get challenged with strain I, and strain I comes from individuals infected with any strain J, tau units of time ago, which now transmits strain I at rate beta ij of tau. And they could transmit strain I because of this within host evolution process that led from infection with strain J to transmitting strain I, provided they have survived background mortality at constant rate mu up to that moment. And then I integrate over all possible times in the past, the duration of the support of these functions depends on which strain you got infected with, because the strain you got infected with tells you how long how infectious you are during your chronic phase, because you have a higher set point viral load, but also how long your life is. And then you sum over all possible infected strains J. The susceptible individuals are the total individuals minus all individuals that are currently infected. So those infected tau units of time ago integrate over time, provided they have survived background mortality. And the total population size changes because of this per capita, total birth rate, per capita death rate, and then individuals that reach the end of their infectious life. So individuals that reach this big TI when they were originally infected with strain I, provided they have survived background mortality, they just suddenly die at the end of their infectious period. So this system is quite complex. It's an equation system with delays. It's just quite complex to study. It can be solved numerically, but it's a bit computationally. But one of the beauties of the system is that you can find the steady state of the system relatively easily without having the full dynamics. And in order to be equilibrium, you can work like this. So this is all H type at steady state. It's a steady state. And you can construct the next generation matrix, which is defined as the total number of individuals of type I infected by an individual of type J throughout their entire infectious period. And R naught is the dominant eigenvalue of that next generation matrix. And now this vector of incidences needs to satisfy, well, if you assume that H doesn't depend on time, from this equation you obtain this system here, where this vector needs to satisfy this eigenvector eigenvalue equation, where this is a number, K is a matrix, and so H needs to be it needs to be an eigenvector of K relative to the dominant eigenvalue of K, which is R naught, and this term in front of it needs to be 1 over R naught, which is compatible with the standard result that the fraction of susceptibles is 1 over R naught in a population at endemic equilibrium. And so you can actually, by just doing linear algebra, once you've worked out this case, which you need to integrate numerically, then you can easily calculate the steady state of the system. In time, host is what really determines these beta ij of tau equations. And here we ended up using a toy model because information is still difficult to collect. But there were 2 fundamental choices at the beginning. First, the ones I've described before, like there is a virus immune system competition model. It's possible to do that, but obviously then you need to solve that numerically, which can be a bit computationally expensive. But in particular, the main reason for not doing that is that it's very little hope to have a simple model that gets you a non-unimodal infectivity profile. They typically have something that grows over time and then comes down. And instead, we know that the profile for H is really exotic shape, where you have a high infectivity at the beginning, then a low value, and then a high infectivity later on. So we went down the route of artificially imposing a shape of this motivated by data on the set point viral load. We assume the duration and the height of these two phases are fixed, and instead the set point viral load determines the height and the length of this intermediate phase. But basically you have an infectivity profile alpha of j, and then we model the within host dynamics in terms of just competition between the two strains, in terms of between the multiple strains within the host in terms of their relative frequencies. And we do that by assuming that of the number of variants of strain I, each strain replicates at a certain rate, which might be different from the different strains. And then there is a mutation matrix, and then Q is the reproduction mutation matrix. And if you just put them together, you get a simple linear system of unbounded growth. But then when you look at the frequencies of each strain, then you obtain what's called a quasi-species equation, which is still linear, but the sum of all of the solutions is 1, stays at 1. And so the link between the within and between host scales is given by this function here, which determines your overall infectivity profile, and it's determined by the strain J that infected you, because I told you that the strain determines your set point viral load, so the height and the length of this phase is determined by these within host equations that determine the frequency of strain I at time t, given you were originally infected with strain J. And we also assume that different strains could be better or worse at transmitting between hosts. And if you list all of the strains from 1 to n, we take the convenient assumption that the strain number 1 is the one that the slowest at replicating, and a realistic number is that there is 1 replication cycle per day. And strain n is the faster at replicating, so either has the same replicative capacity, so all strains are identical, and we linearly, so all of them are identical, or we assume that the strain n is, say, 15% times better at replicating, and all of the other intermediate strains are linearly interspersed between these two extremes. And the between host fitness could be positively correlated, so strain n, which is better at replicating within the host, is also better at replicating at transmitting between hosts, or it could be negatively correlated. And then we can investigate the different contribution of these different factors in the model. So in particular, we focus on 3 within host landscapes. So there's a flat, the flat landscape where every strain can mutate into the strain next to them, either forward or backwards, but they all have the same replicative capacity. Or, as I said, the strain n is the one that replicates fastest, and you can still mutate only to the strain next to you. Or what we call this the hill climb fitness landscape, because naturally you climb up the hill, or a rugged fitness landscape, where again there is this differential replicative capacity within the strains, but also every strain can mutate into any other strain. But in order to reach that, you need to cross a fitness valley, so you need to harbor a double mutation in order to arrive at that point, in which case we get this mutation matrix.
Just a couple more minutes, if that's okay, Lorenzo, just so we have time for questions.
Sorry, 5 more minutes.
Just a few more minutes, yeah, thanks.
Yeah, okay, cool, thank you. And so this is, if you have only 4 infections, you have this infectivity profile, and then in the flat fitness landscape, if you get infected with strain 1, then gradually strain 2 comes in, the frequency of strain 1 goes down, and then strain 3 comes in a little bit, and strain 4 takes a little bit longer. If you were infected with strain 2, you have a higher infectivity during this phase, a shorter life, and then all of the strains can come in because they are equally good at replicating, but they come in very slowly. If instead you have the hill climb fitness landscape, you get infected with strain 1, this goes down quickly, strain 2 comes in and replaces it, then strain 3 comes in and replaces strain 2, and then strain 4 takes over. Because this is the best one within the host, it just takes over everything. If you are infected with strain 2 instead, then strain 1 doesn't come in at all because it's worse than strain 2, but strain 3 comes in and strain 4 comes in and so on, but also you live a shorter life. And so by looking at the respective relationship between the overall infectivity profile and the speed of the within host dynamics, then you end up having really complex patterns of how much you transmit one strain compared. For example, in this case, you get infected with strain 3, strain 4 is better at replicating within the host, but because your infectious life is short, essentially you transmit strain 3 throughout your entire life, while in this case, you get infected with strain 2, but strain 4 arrives quite quickly, and so you transmit strain 4 for most of your life. So there is a complex interconnection between these things. And because I told you that the endemic equilibrium really quickly, then you can easily solve this system even with large number of strains. But I don't want to spend too much time discussing the results of this study, but only to kind of describe the methods. One thing that it's important, I introduced this to say that because the model is more complex, you really need to think carefully about what structural assumptions your model is having, and not really just try to solve the model. You really need to kind of be as smart as you can and understand what assumptions are really relevant. So there are some structural assumptions here. There is no external event. So I'm assuming that once you get infected, nothing happens within the host, apart from the within host dynamics, which are completely autonomous as a process. And so I'm assuming that there is no superinfection. You don't get infected again with a second strain of infection. And this means that I can describe this within host process with this function here as a function of the time since infection. So I can use a time since infection framework. I can use an next generation matrix approach, and within and between host levels are linked, but because there is no superinfection, there is no full feedback loop, there is no evolving population immunity. And the other assumptions are that there's a single variant infection, which is easy to relax if you increase the number of types. And I also assume that all susceptible individuals are identical, which is harder to relax, but it could be done. But that's key to work out the steady state really quickly. So very briefly, I'll finish up with some open challenges. I've described this within and between host models. They have been called nested models, immunoepidemiological model. They can be constructed as long as you define this function here. You need PDEs or delayed differential equations, integral equations to solve them. But one of the key problems of these models is that they typically assume this between scale link, this beta of tau. So open challenges there are terminology problems because this is an interface between two different fields of study. Is there any benefit of using integral equations or PDEs? And this is an open question, but luckily Francesca has joined the group and she knows everything about it. Experimental studies between the scales, in the link between the scales, are few and very far apart, and a lot more work is needed there. And then I'll briefly talked about reinfection before. If you have an acute infection like COVID, then maybe the superinfection problem is not that important. And in fact, for influenza, people like Julia, Vig, and Adam have been working with these reinfection models that have similar problems because you have to study the infectivity at the population level, but also how the susceptibility at the population level evolves. And it has some problems like curse of dimensionality, and so you need strong assumptions to reduce the dimension of the system and so on. But in my case, in the case of chronic infections, then you need to really talk about superinfections because there is a high superinfection rate. A second second strain can be introduced before the infection is complete, and the data is becoming available, as I showed to you in this experiment of ferrets. And this has the same problem of reinfection, but the timing is very important, and this entire time since infection framework falls apart because now you have to keep track of the time since every infection event of different strains. So it's unclear whether you can do the same thing I described before. And so the summary is that the concept of generation time distribution is strongly linked, at least in my mind, with these time since infection models. The time since infection models are harder than ODEs, but have some benefits. They're useful. This is what I focus on the most. They're useful for these multi-scale models and within and between host models, which are probably more useful for chronic infections than for acute infections like COVID. But they can also be useful for acute infections. In the case of COVID, for example, when you're really interested in the shape of this infectivity, for example, contact tracing, optimal timing of testing to keep infection out of closed settings. And the challenges that I can see are that the link between the two scales is almost always assumed, and really a lot more experimental work is needed to match whatever, like, I don't know, viral dynamics within the host with transmission and the transmission rates between hosts. And the concept of generation time also, that was easy in a simple model. Now, for example, if you have this multi-strain model that I described, how do you really talk about generation time of different strains when you can be when there is no superinfection, you still have one strain takes over other. So it's becoming a lot more complicated, a lot more thought is needed there. And then the problem of infection is superinfection, which is just a really difficult open problem. So thank you very much to most of my collaborators, Katrina, Christophe, Francois, and Andrea Pugliese, and the postdocs in my group, Helena, Chris, and Francesca in particular. And thanks to the funders, and thank you all for the attention. And,
thanks very much, Lorenzo. Really great talk. So we've had a couple of questions come in the Q&A, so I'll just read them out to you if that's okay. So the first one, considering a time to infection model that allows for variation between individuals in terms of their infectivity profile over time, if that profile is also correlated with an individual's contact behavior, so not just the within host disease biology, this means that some of the most highly transmitting risk hosts are used up during the initial stages of an epidemic. Can that depletion be captured in a deterministic model, or does a TSI with individual variation automatically mean that one has to do individual-based modeling?
No, so that can be definitely captured with simpler models. You don't need individual-based models. You need to do something slightly different from what I've done here. So here, if you go back to these equations, I'm assuming here that all susceptible individuals are identical. So the susceptible individuals are not distinguished in types. You become a type once you get infected. And this is basically what's helping me solving the system, because it becomes just a linear algebra problem. But if you have different individuals that have different susceptibilities, then the most susceptible individuals get depleted faster, which is what the question is about. And in which case, the problem becomes a lot more complicated. And even with ODEs, you just need to solve, well, the easiest thing to do is to solve the ODEs. It's difficult to find analytical results, and I've been working a lot on that. But it is possible to write these models, but the result is smarter, but there is no obvious analytical closed formula in that case. You don't necessarily need to integrate the full dynamics. You can still kind of solve it using iterative methods, so you can capture it, whether you use ODEs or whether you use time-series infection models, but it's a lot, you end up having to work numerically anyway, but you can still stay away from individual-based stochastic models.
Sure, okay, great, thanks. I'm thinking in the interest of time, we should probably move on. Perhaps you can answer the second question in the Q&A, type it in if you have time.
Yeah, I will, thank you.
Sorry,
So thank you
again, Lorenzo. So